Imagine you are sitting in a dimly lit room, with only the gentle glow from your computer screen casting a soft light upon your face, and I, like a close friend, begin to share with you a wondrous tale about the universe, a story that will make your heart beat faster, that will make you feel small yet simultaneously filled with hope and awe. This story begins in the recent days of 2025, when the community of those who adore the night sky, the astronomers across the globe, suddenly felt a shiver spreading through them. They were restless, excited, as if standing before a door leading to an entirely new world. And the main culprit was a colossal machine, silently hovering in the frigid expanse of space, millions of kilometers away from Earth, that is none other than the JamesWebb Space Telescope. Let us visualize the JamesWebb Space Telescope for a moment, so that you can truly grasp its grandeur. Launched in 2022, after more than 2 decades of preparation and costs amounting to tens of billions of United States dollars, this telescope is not merely a scientific instrument but also a symbol of human aspiration. It journeys far from Earth, away from the bustling lights of cities, away from the warm breath of our planet, to peer deeply into the endless darkness of the cosmos. With its vast primary mirror, coated in shimmering gold, the JamesWebb Space Telescope possesses the capability to gather faint infrared light from the most remote corners, where ordinary telescopes would perceive only a vast black void. And what of its sounds? Well, in truth, it is utterly silent in the vacuum of space, but in the control room at the National Aeronautics and Space Administration's Goddard Space Flight Center, you might hear the excited whispers of engineers, the clicks of mice as data streams in, and the cheers when a new discovery materializes on the screens. In fact, recent updates from 2025 highlight how the JamesWebb Space Telescope has continued to collaborate with other observatories, such as the Chandra X-ray Observatory, to map dark matter distributions in unprecedented detail, revealing intricate webs of invisible mass that shape the universe's structure. From its earliest operational days, the JamesWebb Space Telescope has begun to transform the way we perceive the universe. It makes us, the tiny humans on Earth, feel as though the cosmos itself is whispering ancient secrets to us. And in 2025, those secrets are no longer mere whispers but resounding shouts that leave scientists overwhelmed, their hearts pounding with surprise. They sense that every solid belief about the universe, from the theory of the Big Bang to the lambda cold dark matter model incorporating cold dark matter, is being completely overturned. Allow me to recount the details to you, step by step, so that you can vividly imagine and feel the excitement permeating the laboratories, where coffee grows cold beside towering stacks of documents. To enrich this narrative, consider how the JamesWebb Space Telescope's observations in 2025 have not only confirmed earlier anomalies but also uncovered new layers, such as the detection of population 3 stars, the universe's first generation of massive, metal-poor stars that illuminate the cosmic dawn, providing clues about the primordial processes that forged the elements of life. The story commences in the infancy of the universe, billions of years ago. Picture the universe then as a dark, chaotic night sky, dotted sporadically with faint glimmers from newborn stars and diminutive galaxies, akin to toddlers taking their first unsteady steps in a vast forest. According to our former understanding, the first few 100 million years following the Big Bang, the cataclysmic event that birthed the universe 13.8 billion years ago, should have been a dim, sluggish epoch, with pale light diffusing from primitive star clusters. Can you envision it? An immense, chilly expanse where the echoes of the Big Bang's roar still linger faintly, yet everything remains in a nascent stage, like an abstract painting yet to be fully rendered. Yet, in 2025, supplementary data from surveys like the Cosmic Evolution Early Release Science Program have painted this era in even more vivid strokes, showing how these early structures were not isolated but intertwined in protofilaments that foreshadowed the grand cosmic web we observe today. But then, the JamesWebb Space Telescope delivered a genuine shock. During its inaugural deep space observations in 2022, as data began flooding in images hazy with red and purple specks flickering on screens, the scientists uncovered something utterly unbelievable. They beheld enormous galaxies, far larger than anticipated, existing merely 300 million to 500 million years after the Big Bang. Consider this: the universe at that time was only a few months old, if likened to its 13.8 billion year lifespan, much like a newborn infant. Yet, instead of scattered, tiny galaxies, they witnessed mature, steadfast adults, possessing complex mass and intricate structures. To expand on this revelation, recent analyses in 2025 from the JamesWebb Space Telescope have quantified these galaxies' star formation rates as exceeding expectations by factors of 10 or more, suggesting bursts of activity driven by pristine gas clouds collapsing under their own gravity. At first, everyone was utterly bewildered. In the meeting rooms of astronomical institutes, you could overhear anxious murmurs. Could the telescope be misinterpreting? Are those reddish-purple spots merely closer galaxies obscured by dust? Or is there a calibration issue with the instrument? They re-examined the data night after night, under the cold fluorescence of overhead lights, amid the humming of computers processing terabytes of information. But the more they observed, the clearer the evidence became. Those minuscule bright points were indeed ancient galaxies, billions of light-years distant from us, and they were excessively large and developed for their tender age. Expanding this puzzle, 2025 brought forth refined spectroscopic confirmations, revealing heavy elements like carbon and oxygen in these juveniles, hinting at rapid enrichment processes that challenge our timelines for stellar nucleosynthesis. A quintessential example that stirred widespread commotion is the galaxy from the JamesWebb Space Telescope Advanced Deep Extragalactic Survey, abbreviated as JADES. This galaxy bears the nickname Gades, and the data indicate that its light took nearly 13.5 billion years to reach Earth. That means it formed less than 400 million years after the Big Bang, during the universe's dawn. Astonishingly, the size and mass of Gades rival our own Milky Way galaxy, home to hundreds of billions of stars, swirling through space like a colossal wheel. Under prior theories, that epoch should have hosted only sparse, small galaxies and feeble twinkling protoclusters. But Gades resembles a sophisticated automaton abruptly materializing in an ancient village, appending every established rule. In 2025 updates, the JADES team reported on JADES-GS-Z14-0, the most distant confirmed galaxy at a redshift of 14.32, observed just 290 million years post-Big Bang, with a diameter exceeding 1,600 light-years and unexpected chemical complexity, including oxygen traces detected via the Atacama Large Millimeter Array collaboration, underscoring its precocious maturity. And even more astonishingly, this is far from a rarity. Since 2022, the JamesWebb Space Telescope has identified over 700 similar galaxies candidates initially, exhibiting bizarre traits: excessively grown, prematurely mature, wholly incongruent with standard cosmic model predictions. Initially, scientists presumed only one or two aberrant fish had slipped through the net, but they soon realized these anomalous galaxies were so prevalent as to seem commonplace. In astronomical conferences, the atmosphere crackles with tension, fervent debates, and a blend of exhilaration and apprehension as attendees acknowledge, perhaps there is a profound flaw in our framework. To bolster this, 2025's expanded JADES and Cosmic Evolution early release science datasets cataloged over 1,000 such outliers, with detailed light curves revealing active supermassive black holes at their cores, accelerating growth through feedback loops. By early 2023, the JamesWebb Space Telescope unleashed yet another bombshell. They announced 6 primordial galaxies, each comparable in size to the Milky Way, existing a mere 500 million to 700 million years after the Big Bang. Per the prevailing model, such titans could not manifest when the universe was under 1 billion years old. The stars within them were fully formed, many aged red giants blazing fiercely, as if the cosmos had sprouted silver whiskers in an instant. Researchers candidly admitted, this discovery poses a major conundrum for science. Some even declared we may need to rewrite the textbooks of cosmology. Envision the old volume narrating diminutive galaxies gradually merging, only for these uninvited behemoths to crash the party, hosting maturity ceremonies before the universe reached 5% of its lifespan. It is akin to toddlers in a nursery class where a few 2-meter-tall, wrinkle-faced elders suddenly stride in the teacher would be profoundly stunned. Furthering this in 2025, the detection of little red dots, ultra-compact, intensely red sources potentially harboring supermassive black holes or dense starbursts has multiplied the tally, with over 300 identified, each defying size limits and suggesting explosive early mergers. Astronomers scratched their heads in perplexity, striving to explain, did theories underestimate initial star formation rates? Or is there an enigmatic acceleration mechanism? Even a bold hypothesis emerged: our estimate of the universe's age is erroneous, and it is far older. The emotions in the community were chaotic exhilaration over fresh insights, yet anxiety as foundational knowledge wobbled. In 2025, simulations incorporating JamesWebb Space Telescope data proposed that dark matter halos formed denser than anticipated, funneling gas efficiently and igniting hyper-efficient starbursts, though these tweaks strain the model's parameters. Then, in 2025, the latest observations left everyone breathless once more. This time, it was a colossal spiral galaxy named Big Wheel, the moniker evoking an immense cosmic roulette wheel spinning wildly in the void. Big Wheel lies approximately 11.7 billion light-years from Earth, its light emanating about 2 billion years after the Big Bang. At that juncture, most galaxies remained petite, just beginning to coalesce. Yet Big Wheel shatters every norm, a fully formed spiral disk structure, exquisite in its beauty, spanning 100,000 light-years in diameter, rotating at 200 kilometers per second, with a mass roughly 5 times that of the Milky Way. It rivals the largest, most evolved spirals of the present day. Discovered serendipitously near a bright quasar at redshift 3.25, its disk confirmed via integral field spectroscopy reveals ordered rotation and a settled stellar population, defying expectations for such an early epoch. Scientists gazed at Big Wheel's image on their screens, swirling luminous arms against an ebony backdrop, and could scarcely credit their eyes. A professor from the California Institute of Technology exclaimed, "This may be the earliest large spiral galaxy ever detected, utterly unprecedented." Another astronomer likened it, "It is like discovering a surviving dinosaur in an era long after their extinction." According to legacy knowledge, 2 billion years post-Big Bang marked childhood. How could mature dinosaurs frolic? In 2025 publications in Nature Astronomy, the team detailed how Big Wheel's environment, an unusually dense protocluster with galaxy overdensities exceeding 10 times the mean, fostered relentless gas inflows and frequent mergers, akin to a fertile nursery accelerating evolution. Yet this localized boon fails to account for the ubiquity of such precocity across JamesWebb Space Telescope fields. To elucidate, the research group conjectured that Big Wheel resides in an atypically dense cosmic region, with surrounding galaxy densities over tenfold the average. Such a milieu acts like fertile soil. Cold gas continually inflows to nourish, frequent mergers propel mass accumulation. This seems plausible for an isolated case, but Big Wheel is not solitary. Over hundreds of other early galaxies spied by the JamesWebb Space Telescope similarly surpass forecasts. Thus, the issue transcends individuality. It implicates the whole. Are our theories fundamentally awry? Supplementary 2025 findings from the European Space Agency's collaboration reveal analogous disks in Zhulong, the most distant spiral at even higher redshifts, with well-defined arms and ancient bulges, amplifying the chorus of descent. Now, let us discuss the lambda cold dark matter model of cosmology, the standard, elegantly simple yet potent formula. It comprises dark energy constituting approximately 68%, cold dark matter 27%, ordinary matter 5%, plus the Big Bang 13.8 billion years ago, alongside gravity and expansion. This model elucidates everything from the subtle cosmic microwave background radiation to galaxy distributions, aligning astonishingly with large-scale observations. Its cosmic history unfolds thus, commencing in searing heat, expanding, birthing light elements, with minute density ripples. Roughly 38,000 years later, dark matter dominates, clumping matter into galaxy precursors. The inaugural stars and galaxies emerge around 500 million years hence, merging into clusters, while dark energy hastens late expansion. Yet 2025 refinements, incorporating JamesWebb Space Telescope baryon acoustic oscillation mappings, affirm the model's backbone while pinpointing tensions in small-scale clustering. But the JamesWebb Space Telescope proclaims, something is amiss. These prodigious early galaxies do not conform. They could not amass so swiftly in 2 billion years to forge spirals. The 6 super-sized galaxies at 500 million years resemble geriatrics in a bassinet. Scientists ponder, was primordial star formation underestimated? Does the initial stellar initial mass function differ, permitting rapid stellar and black hole evolution? Or accelerated mergers via dark matter? They endeavor to patch the lambda cold dark matter model, but if insufficient, cosmology's bedrock crumbles. Science's annals brim with precedents. Late 20th century dark energy detection compelled adding lambda. Now, JamesWebb Space Telescope galaxies may herald an upgrade. Indeed, 2025 hydrodynamic simulations, calibrated to JamesWebb Space Telescope inflows, suggest enhanced feedback from early quasars could quench or boost growth variably, offering a partial salve. Beyond galaxies lies the Hubble constant scandal, the universe's expansion rate, measured disparately, one via nearby supernovae, another from cosmic microwave background. Dubbed the Hubble tension, it ranks among major enigmas. Some suspect dark energy is not constant but dynamic. In late 2023, Adam Rees Nobel laureate for accelerated expansion discerned fresher JamesWebb Space Telescope data on Cepheid variables and distant supernovae with superior precision. The discord sharpened. Rees queried, why do premier tools disagree? Perhaps dark energy was stronger primordially, waning to explain local speedup. Or vice versa. Analogy, expansion like an automobile accelerating, with the throttle variably pressed. If lambda varies, the model metamorphoses. 2025 brought pivotal turns. The supernovae Hubble Space Telescope Open Extragalactic Survey and JamesWebb Space Telescope crosschecks yielded a Hubble constant of 70.4 km per second per megaparsec, bridging prior gaps from 67 to 73, though debates persist with the Chicago Carnegie Hubble program advocating resolution via infrared calibrations, while others like the Simons Observatory anticipate further cosmic microwave background. Polls to adjudicate. Most recently, updates from the National Aeronautics and Space Administration and the European Space Agency in 2025 demonstrate the JamesWebb Space Telescope persistently validating thousands of early galaxies through expanded cosmic evolution, early release science and JADES initiatives, with enhanced spectroscopic resolutions solidifying anomalies. The Hubble tension endures, with fresh JamesWebb Space Telescope metrics pegging the Hubble constant at approximately 73 km per second per megaparsec, diverging from Planck's 67. Moreover, the telescope's inaugural exoplanet imaging of TWA-7b in June 2025, a young gas giant orbiting a nearby star, underscores its versatility in probing habitable zones, intertwining exoplanetary and cosmological quests. As venerable theories face challenge, imagination erupts. One notion, our universe resides within a colossal black hole. In 2025, JADES revelations showed 2/3 of 263 distant galaxies rotating clockwise, 1/3 counterclockwise, not the 50-50 randomness of isotropy. This hints at a preferred cosmic spin, contravening the model's uniformity. The black hole cosmology theory posits our universe inside a parent cosmic black hole. When a massive star collapses, no singularity forms. Instead, it rebounds into internal expansion, mimicking the Big Bang. The event horizon bounds observability. The parent black hole's spin axis imprints a legacy, elucidating galactic spin biases. Ideas from Raj Pathria and Nikodem Poplawski. If veridical, black holes cradle nascent universes, stacking like Russian nesting dolls. The sensation is majestic, spine-tingling. Echoing this, 2025's detection of interstellar comet 2/2 Echabit-Sivo, observed in August, offers pristine samples from another stellar system, potentially bearing organic precursors that seeded our solar system's complexity. Another theory, timescape cosmology. Time flows variably across cosmic regions per Einstein's gravity. In dense locales like galaxy clusters, time dilates; in voids, it accelerates. Type Ia supernovae sightings from sparse voids appear distorted, misconstrued as accelerated expansion. No dark energy needed, merely an illusion from inhomogeneity. Analogy: cosmic time zones, with clocks askew fostering illusions of time travel. 2025 void mapping via JamesWebb Space Telescope and Euclid satellite lent tentative support, revealing luminosity discrepancies aligned with density gradients. Finally, challenging the Big Bang itself. Was it truly a singular origin? Or multipoint, inflationary bubbles? Cyclic universes, bang expand contract rebang eternally, as in Penrose or Steinhardt models. Early galaxies, perhaps relics of prior cycles. Black holes birthing galaxies. Black holes precede, aggregating matter. White holes, black hole inverses, ejecting matter, perhaps igniting the Big Bang or local galaxies. All preserve the hot, dense, expanding primordial cosmos but unveil novel paths. Science evolves incrementally, mending rather than demolishing. The James Webb Space Telescope shocks, yet data scrutiny persists. Accurate redshifts? Radio corroborations? Adjustments to lambda cold dark matter via efficient star formation, bespoke environs may suffice. But systemic quirks herald revolution akin to Kepler's ellipses, quantum mechanics, Big Bang supplanting steady state. In 2025, the Sagittarius B2 molecular cloud imaging unveiled a kaleidoscope of massive stars and luminous dust, illuminating starbirth cauldrons that mirror early universe processes on grander scales. The future beckons. Textbooks a decade hence may narrate how the James Webb Space Telescope in 2022 unveiled anomalies, birthing a refreshed portrait. Black hole universe? Timescape? Or unimagined? Science self-corrects, drawing nearer truth. Are you prepared for the next chapter? The cosmos awaits exploration, and the James Webb Space Telescope but scribes its preface. Thrilling, is it not perhaps the truths we cherished were amiss, but emergent verities more sublime?